Hello and welcome. Today we're diving into the world of semiconductors, specifically looking beyond traditional silicon to two exciting materials: gallium nitride, or GaN, and silicon carbide, known as SiC. These aren't just incremental improvements, they represent a major leap forward in power electronics. The key difference lies in something called the band gap. Think of it as the energy needed to get electrons moving and conducting electricity. Silicon has a band gap of about 1.1 electron volts. GaN and SiC boast much wider band gaps, around 3 times higher, at 3.2 to 3.4 electron volts. This fundamental difference is why they're often called wide-bandgap, or WBG, semiconductors, and it unlocks significant performance advantages. So what do these wider band gaps allow? First, GaN and SiC devices can handle much higher voltages within a smaller size compared to silicon. Second, they are incredibly resilient to heat, operating reliably at temperatures up to 200 degrees Celsius or more, far exceeding silicon's limits around 150 degrees. This simplifies cooling and boosts reliability. Third, they can switch on and off much faster. GaN, in particular, excels here, enabling switching frequencies in the megahertz range. This speed leads to the fourth major benefit: higher efficiency. Faster switching means less energy wasted during the switching process, and lower resistance when conducting current minimizes energy loss. Finally, combining higher efficiency, less heat, and higher frequency operation, smaller components like capacitors and inductors, results in significantly greater power density. This means smaller, lighter power supplies and devices for the same power output. While both GaN and SiC outperform silicon, they aren't interchangeable. They have complementary strengths. Gallium nitride, or GaN, is the speed champion. It's fantastic for high-frequency switching, leading to very efficient power conversion. You'll typically find GaN in low to mid-voltage applications, up to around 650 or 900 volts. Think fast chargers for your laptop or phone, efficient power supplies for data centers and telecom equipment, high-fidelity audio amplifiers, and, increasingly, onboard chargers and converters in electric vehicles. A key advantage is that GaN can often be grown on existing silicon wafers, potentially lowering costs. Silicon Carbide, or SiC, on the other hand, is the high-voltage workhorse. It excels above 900 volts, routinely handling 1200, 1700 volts, or even more. SiC is also very robust and has excellent thermal conductivity, meaning it dissipates heat effectively. This makes it ideal for demanding high-power applications, like the main traction inverters that drive the motors in electric vehicles, EV fast-charging stations, large-scale solar and wind power inverters, industrial motor drives, and power grid infrastructure. Manufacturing these advanced materials isn't as straightforward as silicon yet. Producing high-quality SiC wafers is complex, though costs are coming down. GaN is usually grown on other materials, like silicon or SiC, with GaN on silicon offering a cost-effective path using existing infrastructure. Controlling defects during manufacturing is crucial for both materials. Despite these hurdles, progress is rapid. The market is booming, driven by electric vehicles, the need for energy efficiency in data centers, and renewable energy growth. We expect costs to continue falling as production scales up, potentially reaching parity with silicon in some areas. Performance will keep improving, and we'll see more integration, like GaN chips combining power stages and control logic. Research is even looking beyond GaN and SiC to materials like gallium oxide for future breakthroughs. In essence, gallium nitride and silicon carbide are revolutionizing power electronics. GaN brings speed and efficiency to mid-voltage applications, while SiC provides the robustness needed for high-voltage, high-power systems. Together, they are enabling smaller, lighter, and vastly more energy-efficient devices, paving the way for a more electrified and sustainable future. Thanks for tuning in.